Yeah, hi everyone. Thank you for coming to this talk. And the title is Advancing Cyberbullying Detection with Psychological Insights and Complex Media Data. So the works I'm going to introduce today are all from my PhD study, and some of them, most of them are my first author papers, and some of them are my students, like who have worked with me together to on this project. So what is cyberbullying? Cyberbullying is any type of harassing, threatening, demeaning language, typically done through mean comments, online rumors, and sexual remarks. And certainly, it's one of the most pressing online risks for young people, as shown by the following striking cyberbullying facts. For example, 7 out of 10 young people experience cyberbullying before they hit the age of 18. So the question is why the research question is why now? Why can we simply use a standard text classification or binary classification model to solve this problem, right? So as shown by the emerging definition in social psychology, there are 2 unique attributes of cyberbullying behavior. So one is repetitive pattern. Basically, it says that cyberbullying is an aggressive and intentional act carried out by a group or individual using electronic forms of contact repeatedly or over time against a victim that cannot easily defend him or herself. So from this definition, from social psychology, we can see there are 2 unique attributes: repetitive pattern and the power imbalance between the bullies and the victims. So in order to study these unique attributes, so the first thing we need to do is, instead of looking at the single piece of text as the input, we need to look at a higher level, the social media session level, or a social media post. For example, on the right-hand side is a Instagram social media session, and someone posted an image, and there is a sequence of comments arriving over time, right? So each of the comment has the temporal information, and we also have the other social content information, such as number of likes, number of shares. And certainly when you look at these comments, there are some words and some comments are more relevant to the cyberbullying behavior. So let me first define this new problem of session-based cyberbullying detection. So given a corpus of social media sessions and the corresponding label y, so the y is a binary variable with 1 denoting bullying and 0 otherwise. So our goal here in this session-based cyberbullying detection is to identify a cyberbullying behavior within a social media session by leveraging all these different various information in the social media session, such as these textual features and user interactions, spatial location, temporal information, and even images and social network and other social content, such as user profile information. So we want to learn a mapping function that can map the original social media session into a binary variable 0 or 1. So that's the task. And then what are the unique challenges, or we could say the opportunities, right? So with this social media session or social media post, we have several unique attributes or challenges to solve, to address. First one is multi-modality. So in the social media session, we have different multimedia objects, such as image, we have time information, spatial location, and textual information. And then the second one is the temporal dynamics. Basically, for each of these comments, they have it has a temporal information, right? The timestamps. So, and also these comments arriving over time. So there is a temporal dynamics or evolution in this social media session. And then another challenge is how the structural information, how do we model this social media session? So the hierarchical structure here, I mean, we have a sequence of words can form a comment, and then a sequence of comments can then form a social media session. And certainly some of the words and some of the comments are more important for us to identify cyberbullying behavior. So that's why we also need attention to focus on those more important words or comments. And the last one is user interaction. So how people, like, as I mentioned earlier, we have this, the unique attribute is a repetitive pattern, right? So how these users, how do they interact, and how this repetitive pattern can be reflected in this user interaction, as well as their discussed topics. So here are just the four challenges and opportunities that I have solved. So these are the challenges I have tried to solve, and of course there are more challenges. And so let's first start with this multimodality. So this work is actually my first my first paper on cyberbullying detection. And so this paper is about cyberbullying detection within a multimodal context. So for each social media session, we have different modalities. And so the first question you probably want to ask is, why do we need to consider these multimodalities, right? So there are several reasons. One is, for cyberbullying behavior, there are multiple ways of cyberbullying behavior. For example, we have humiliating images and insulting comments or hashtags or fake profiles. And also these multimodalities can provide complementary information to help understand user behavior. And then the next question is, how do we leverage this multimodal context? When we answer this question, we are actually, what we are actually answering is, what are the challenges in order to model these multimodalities? So one challenge is there is heterogeneous information. So the heterogeneous information means we have information from different modalities, and this information may not be compatible with each other. And the other challenge is social media data are often non-IID data. So, and it's often intrinsically correlated. And for example, the social network information, like social network is not IID because people, like users on social media, they are often like connected to each other, right? And then the third challenge is different modalities are frequently associated with very diverse feature types and high dimensional. So like, for example, the text is usually very high dimensional, and some of the features are very diverse, have very diverse values. For example, the temporal information and the location. So to solve these, to address these challenges, we have this propose a framework which calls cross-bullying, the title, the X-bully, cross-bully. And then in this framework, basically the first challenge we need to address is how to find out the reduce the feature value. As I mentioned earlier, we have very diverse feature values, right? So the first challenge we need to address is how to using a more effective way to reduce the feature values. So here our solution is to use a kernel density function for each mode. The mode here means that we have image and we have temporal information. So each of these kind of information belongs to a mode. And then for each of these modes, we want to find the spots that have highest density or very high density. So here is, that's why we have these mod hotspots. We first propose this definition of mode hotspots. So given a corpus of social media session, the mode hotspots for a mode M, so the M can be the image or the location, are the set of local maximums of the kernel density function estimated from this specific mode. So here, just give you some high-level stuff. So here, this just a kernel density function, and then the k here is a kernel function, and here this sigma m is this kernel bandwidth. Basically, it's a smoothing parameter. And n is the sample size, like how many social media sessions we have. And then we can identify the mode hotspots using a mean shift algorithm. So this mean shift algorithm is based on a previous work. So after we have these, find out these mode hotspots, what's the next step? So in each of these social media sessions, right, we have different modes, modalities, and then the next step is how we want to construct a network from these social media sessions. But the question is how. And as we can see here, for each of these social media sessions, we have one relation. That's the coexistence relation, means that the user and the text information, if they are in the same in the same social media session, then we say there is a coexistence relation. And then for the relationships between different social media sessions, we define this neighborhood relation, meaning that for the same mode between different sessions, we then define a weight or strength or kernel strength to describe how close or how similar these two values are. So for the same mode, they have in the different social media sessions, they have this neighborhood relationship. And then we also have, among all these modalities, we have attributed modality, and we also have non-attributed modality. So what I mean by attributed modality is that this time from, like, for example, the time and the image, they have exact values. But for the non-attributed modality, I mean, like the user. So user, we just, in a social network, we use an index to represent a user. So that means these are the non-attributed modality. So for all these modalities, we use this mod detection method, hotspot detection method, to find out the mod hotspots for each of the mode. And then, so we have all the hotspots, right? Here, the user and the time hotspots and popularity hotspots. So the next step is to leverage this coexistence relation and neighborhood relation to build a graph, a network. And this network is heterogeneous network. Why it's called heterogeneous? Because in this network, we have different node types, and we also have different edge types. So now we have this heterogeneous network. And then the next step is how to learn. So basically the cyberbullying section task is we want to learn a representation from each social media session, and then use this representation to for the prediction task, and then to train a classifier and to do the prediction. So with this heterogeneous network, what we really want to learn is a representation of each social media session, right? So how to learn this is we build this heterogeneous network, and then we can see, then we have different sub-network because we have different node types, and then we can extract all these sub-network to learn a joint embedding for this social media session. So for example, suppose it's Instagram session, we have 5 different modalities like user, image, profile, time, and comments or text. And then there are different types of edges. So by leveraging the coexistence relationships, we have 10 types of edges. Basically, it's 2 from 5, right? to choose. So basically, we have the user image and user profile relation, and we also have time and comments relation, etc. So totally, we have 10 types of badges with the coexistence relations. And we also have neighborhood relations. There are four types of neighborhood relations. Basically, we have user and user relation, and image and image relation, etc. And then with this, we built a heterogeneous network, and we extract a subnetwork with different node types and different edge types. And then we can learn a embedding for each of the node, for each of these node. For example, I can learn a node representation for the time, and also the representation for an image. But then the question is how to construct a representation for the social media session. And so a straightforward way is basically to concatenate or sum up all the representations for each of these specific modality. For example, a social media session can be represented by the concatenation or summation of all the representations of all these different modalities. And then we can, with this, we learn a representation for each of these social media sessions. And then the next step is just to train a classifier. It can be any machine learning classifier, such as support vector machine, and to train this classifier using the representation we learn, and then to do prediction. So the data set we use are the two benchmark data sets for cyberbullying detection. There are Instagram data and there are Vine data set. So the Vine data set, they have very similar formats. These two data sets have very similar data formats, but they they're collected from different social media platforms. And also, as you can see, for the real world data sets for cyberbullying detection, most of the sessions are non-bullying sessions. Basically, it's a very imbalanced data set. And for evaluation metrics, right, we consider some standard classification metric, such as macro and micro average F1 scores. And the difference is for the micro, the MACRO F1 score, is calculated independently for each class. And then we take the average. The micro average F1, the second one, MICRO, we aggregate the contributions of all classes and then to compute this average metric. So in the binary classification case, the micro average F1, the second one, is equal to the accuracy. So yeah, here I just to show the results for the Instagram data. And the Vine dataset, you can feel free to refer to the paper. So here, the baseline models we consider are the sum of the network embedding methods, because basically our model is also a network embedding method to learn the representation, right? And also the difference is we consider the heterogeneous network embedding instead of like the traditional network embedding methods that treat all the nodes and edges equally. So we compare those traditional networking embedding methods, and then they also learn the representations for each social media session. And since this is a classification task for each of these, so for each of these baseline models and our model, we need basically need a classifier, machine learning classifier, in order to do the prediction. So for the classifier, all the input are different. So there are different representations learned from different baseline models and our models. But the classifier is the same, right, for all the different baselines. And then the percentage here means that we use the proportion of data sets we use for training. So 10% means we only use 10% of the data sets for training and the rest for testing. And then also we compare with the then state-of-the-art cyberbullying structure model, like the last two rows are the state-of-the-art cyberbullying structure models. And then we can see our models can mostly achieve the best performance regarding the different evaluation metrics. And also when there are more training data we have, and we very clear observation is that for all the models with more training data, the performance can increases. And our models can achieve the best performance regardless of the percentage of training data we used. So that's multimodality. And we still have some other challenges to address. For example, the temporal dynamics and the hierarchical structure and the attention. So next I will introduce a work. Actually, it's journal paper which is an extension of a previous the conference paper. And so as I mentioned, we have several challenges, right? To address those challenges, we propose a first bottom-up structure to model this social media session. That means we leverage a hierarchical attention network. Basically, it has both word level and common level encoder and attention mechanism. And then the goal here is to learn a session representation, which will be used for the final classification task. More specifically, the encoder is basically a bi-GRU-IN, so it can capture the bi-directional contextual information. And then we also the attention mechanism is an additive attention mechanism. We assume there is a latent vector, UW here, can capture all the contextual information in the comment. And then the attention weight is calculated as the similarity between the word representation and this latent vector. So after we calculate this attention weight, the comment representation would be the weighted sum of the word representation. And similarly for the session representation, the next level, right? After we learn the comment representation, the next level is to learn the session representation. And similarly, the session representation would be the weighted sum of the comment representations. But more importantly, we want to model these temporal dynamics in the social media session. Informed by the previous findings, such as cyberbullying takes place across a stream of comments that are typically relatively close in time, and also the finding that the time intervals between consecutive cyberbullying comments are usually shorter, in bullying sessions are usually shorter than those in non-bullying sessions. So here, the first framework solution we propose is a multitask learning framework. Basically, we have one task of predicting the cyberbullying label, and the other task is to predicting the time intervals between the consecutive comments. So by exploiting the commonalities and the differences between these two tasks, we can learn more generalizable features. So that's the first solution. And basically the first solution is we try to extract some of the temporal information from the social media session and then to model the user commenting behavior. But can we directly encode the temporal ordering of the comments? So as we shown in the preliminary results, we found that there is a periodicity in the comment count. So this informs us to use a trigonometry function such as sine and cosine to form a geometric progression. And the goal here is to learn the temporal representation. And then for the comment representation, it's then the concatenation of the content representation C here, Cj, and the temporal representation P here. So basically the comment representation consists of both the textual information as well as and this temporal information. So for the evaluation, we have still we use the instrument data, the benchmark data sets, and most of them are non-Boolean sessions. And then for the baselines, we include the standard text classification models, and as well as deep learning models and some of the state-of-the-art cyberbullying detection models. Since this is a classification task, we include standard classification metrics such as precision, recall, F1, and AUC scores. So the larger these scores are, the better the performance is. So now let's first see the results for the real-world data sets. Basically, it's a very imbalanced data set, right? And then what we can see here is our two models, the proposed two models. One is the multitask learning framework, or the HNCD here, and the direct temporal encoding of the temporal ordering, which is the HNT model here. Our two proposed two models can outperform all other baselines in terms of predicting the cyberbullying behavior in a social media session. And we also show this multitask learning framework, HNCD, can show better performance than the direct encoding of this temporal ordering method. And we believe this is because this multitask learning framework can help us to learn more generalizable features. So this is for imbalanced data. But so if we train our model on imbalanced data, the chances, the possibility, it's possible to for these machine learning models to learn very skewed patterns that may not be effective for detecting cyberbullying. So what we can do is, how about we train our model on a balanced data set? Basically, we can do data augmentation or data oversampling to make sure that the positive instances or the bullying instances equal to the non-bullying instances. And then we still test our model on the real world data sets or the imbalanced data. So we use a common data augmentation algorithm, SMOT, and to do oversampling. And we still test it on the imbalanced data set. So from these results, we can see that in addition to the observation that our models, the HNCD and HNT, can still show better performance than other baselines. What's more interesting is when you compare this standard classification model, we can see by training on the balanced data, their performance can improve a lot. And while for this deep learning based model, if you train the model on the balanced data, their performance barely changes or even decreases a little bit. So we believe this is because when we do the data augmentation, the SMOT algorithm is basically a simple linear interpolation method. So that means it can disrupt all the structural dependencies in a social media session between the comments. And these deep learning models highly rely on those structural dependencies to make accurate prediction. So from these two sets of results, we have some key observations. One is by modeling temporal patterns, we can help capture the unique attribute of cyberbullying behavior. That's the repetitive pattern, and which can result in more accurate prediction performance. And the second observation we have is this multitask learning framework is more effective than direct encoding of the temporal representation and then combine it with the content representation. So this is because the multitask learning framework can learn better, can learn more generalizable features. Last but not least, the observation is important observation is that maybe we need to shift our focus of AI researchers and practitioners from model development to the quality of the data we use to train the model. And as we shown in the results, that if you simply do data balancing to augment the data the standard classification model can largely improve their performance. So here, this also answers the call to the data-centric AI, which is a campaign launched by the AI pioneer Andrew Ng, among others. So the last one is about the user interaction. Understanding user interaction is very important. There are several reasons. For example, from our preliminary results, we show that by modeling these user interactions in each social media session, basically to look at how who this user is replying to or tagging, and then we use this constructed network, and we show that there are different intensities of user activities in a Boolean session and in a non-Boolean session, as shown in the first figure here. And we also need to categorize the repetitive pattern, right, in the social media session, and to capture those temporal analysis. As shown in this, the second figure in the social example of the social media session, we can see in the Boolean session, there are multiple Boolean comments appearing over time. And this understanding user interaction is important because we can also help monitor the user's time involving roles. So for each social media user, they might have different roles. For example, they can be bystanders, they can be bullies, and they can be victims at different time points. So understanding user interaction is important. And then the question is, how can we model this user interaction? So here is basically a framework, and which is called a TG-Bully, temporal graph-based cyberbullying detection. And so it has several components. Like first one is the semantic context modeling. Basically, we want to model the semantics in each social media session, and then we have this in order to model this user interaction, and specifically this repetitive pattern and the temporal dynamics, we need to we then propose to construct such a temporal graph interaction learning method to learn the representation for each of these user or the comment. And then the next step is to do session classification. So for the semantic context modeling, here it's we have two different context information. One is the comment. So in the social media session, we have different comments, right? And then we have these. We also have the information for each user. So we have the historical comments that each user posted before. So we have these two types of contextual information, the comments and also all the historical comments posted by each user in a social media session. So for the comment encoding, we use a hierarchical attention network to model this comment, to learn this comment representation. And then for the historical comments, we also use this hierarchical attention network, but it has this comment, a sequence of words can form a comment, right? And then a sequence of comments can form the historical, like a user can post a sequence of comments. And then basically we used this hierarchical attention network to learn both the comment representation and the representation of the historical comments posted by each user. And the advantage of using these historical comments is we want to capture the user's language behavior and personality traits reflected by their historical comments. So now we have, for each of these nodes here, the R here is the user representation, learned from both the comment representation as well as their historical comments representation. So each of these nodes here is the representation of each user. And then the next step is to construct a graph. And also it's a temporal graph because we also need to consider the temporal dynamics in each social media session, right? So here we propose to propose a temporal graph. Basically, the node is a user comment representation, and the edges are the interaction between the users or the comments. So, and for each of the edge, we also have the weight. And so here is, for example, the T1, 2 meaning the temporal, the intervals between the comments or the user R1 and the user R2. So what's the time interval between these two comments posted? And then we use this graph attention network to learn this node representation. For basically, we leverage this graph attention network to learn the representation for each of these nodes, and because we consider the temporal information, right? So the advantage of the reason that we use the graph attention network is because it can automatically learn the attention weight for each of the nodes. And then based on this, we can capture the topic similarities between the comments. And in the also, our graph attention network is different from the traditional one because we also include the temporal dynamics. Basically, that's the temporal intervals, the intervals between two consecutive comments. Not necessarily consecutive. Basically, it's the time intervals between two comments in a social media session, and then we incorporate both the topic coherence or the topic similarities between two comments and the temporal dynamics into this graph attention network. So the goal here basically is to learn the representation to further learn the node representation for each of these users. And the last step is to do session classification. So the question is, we now have different user representations, right? We have the history representation, which is learned by the historical comments. And we also have the graph representation version of each user, which is learned by the previous graph attention network. And then we need to, we use a gated mechanism basically to merge these two user representations. And then the session representation would be similar to the attention network. We use these attention weights to sum up all the user representations and then to form a social representation, social media session representation. So as you can see, the important thing in this session-based cyberbullying detection model is basically how you learn very high quality representation of each social media session. So here we show some the results, and still the data set is the Instagram data, and we use complete and half Instagram data for training. Basically, we want to see how, like, if we use less data, how our model perform compared to other baseline models. So we here we include the standard text classification model, deep learning model, as well as these state-of-the-art cyberbullying detection models. And then we show our models can mostly achieve the faster performance, especially when we have larger data sets for training. And then we also show some interesting case study, right? So here are the two sessions. One is the bullying session, one is the non-bullying session. And we showed that our model can accurately identify the words that are more relevant to cyberbullying, and also the comments that are more important to cyberbullying behavior. In addition to that, we can see these green grids here, the matrix here basically shows the graph weights between the users. So we can see in the bullying sessions and non-bullying sessions. For the bullying session, the weights are more diverse, right? And for the non-bullying sessions, they are more uniformly distributed. So that means our model, this graph attention network, can help capture the topic coherence as well as the temporal dynamics. So we already talked about these four the unique attributes, the challenges of this social media session, like the temporal dynamics, the multimodality, and the structural information, as well as the user interaction. But what's next? So here is a work that's published last year at ACL. And so the motivation of this work is to that in recent, we have the recent findings have shown the standard model, like machine learning classifier, will show discrimination against some certain demographic groups. For example, here, if a tweet or a comment is written in African American English, it has the classifier has much higher confidence identifying it as a toxic or hate speech, even though it has nothing to do with toxicity. So the question is, do we have similar issues in the session-based cyberbullying section problem? So, and the question, also, if there is indeed such a phenomenon, what would be the unique challenges to debiasing such classifier? Because we have such social media session, which includes a sequence of comments, that's sequential data. So for the first question, the answer is yes. We observe a large performance gap between these sessions, including those sensitive triggers, such as Black or gay, and sessions without those sensitive triggers. So you can see on the bottom, the figure on the left-hand side, you can see there's a huge performance gap between these two types of sessions. And then after we debiasing, the performance gap is largely reduced. So the task here is we want to learn a accurate, but also more importantly, a less biased binary classifier, cyberbullying detection classifier that takes input of social media session. So why can we simply use existing bias mitigation approach to solve this problem? The challenge really arises from this specific social media, the data format. We have this social media session, and it has sequence of comments. That means these comments arriving over time, and when we make we need to make dependent decisions. So that means when we make a currently when we make a decision, this decision will influence future prediction as well as their debiasing strategies. And some other bias mitigation approach, such as data augmentation methods, are not applicable in our task, because first of all, if you do data augmentation, it's possible it will result in meaningless comments. And also for each of these social media session, it has it can be the number of comments can be very large. That means if we use data augmentation algorithm, it can be very computationally expensive. And this method also is limited to the social categories the social identities with a few categories, such as gender, but what about race? So to assess bias, we use false negative and positive equality difference to define these bias. Basically, you can see we want to we want to minimize these differences, right? The difference of the false negative rate calculated over the sessions, including those sensitive triggers, and the false negative rate calculated over the entire training data. So we want to minimize the differences in order to reduce the biases. Then for bias mitigation, since, as I mentioned earlier, we are making a dependent decisions. So that means the current decisions will influence future decisions. So naturally, what we leverage is a reinforcement learning framework, and specifically it's a sequential Markov decision process, and it consists of different components. For example, the agent is a biased classifier, and its action is to predict the label. But the most important component in this framework is the reward function. So it has two components. One is regarding the prediction error. So we want to minimize the prediction error, right? And then the second one is the bias term. So we propose to use a harmonic mean for harmonic mean of these previously introduced the two bias metrics as the bias term. So by maximizing this reward function, then we can learn a debiased cyberbullying classifier. So this framework is model agnostic, meaning that we can take any biased classifier as the input. And then it's also context aware, because at each moment we make a decision, we need to consider all the historical comments. So the first question is, can we mitigate this unintended bias, right? So we compare our models with biased model, as well as the state-of-the-art fair machine learning model for cyberbullying detection. And then we show that our debiasing strategy can significantly reduce the biases compared to other baselines. And then we further show our debiasing strategy can indeed reduce the biases against those sensitive terms such as gay, black, and the N-word. In the bias and fairness literature, a frequently discussed question is, do we have the trade-off between the accuracy and the debiasing? So in contrast to most existing findings that there is indeed a trade-off, our models can achieve both. We have less bias, and we also can improve the prediction results. So the broad result of our model is that reinforcement learning can be very useful to debias for the sequential data, as it's all about making dependent decisions. And this also further indicate that the context plays a significant role in bias mitigation. And this is also shown by the previous works in bias and fairness literature. So what's next? There are still many challenges that we need to address. For example, in the bias and fairness for fair machine learning models for cyberbullying detection, what we haven't touched is, for example, the bias correlations. We show in a work that is currently in submission that if we, for example, if we try to use a model to debias gender, actually this debiased model can also influence other type of biases, such as race and religion. And also there is intersectional bias, right? Such as African-American male, African-American female. So in this work, these authors show that for the intersectional bias, if we consider intersectionality, the bias is even worse than a single type of bias. The other challenge that we need to address is the generalizability problem. So there are many, actually, a lot of work have shown that if we deploy the machine learning, like cyberbullying detection models or hate speech detection models to deploy it in a open networking environment or in another social media platforms, their performance is largely reduced. So generalizability is a very important task that we need to address, we need to solve. And then, so there are several types of generalization. For example, there is what I mentioned earlier is the generalization across different platforms, right? There are also cross-lingual generalization. Mostly the current work so they focus on English, but what about other linguists, like other languages? So there is also a cross-lingual generalization. And then there is also a small data challenge, meaning that we don't have enough label data for cyberbullying detection or hate speech detection, partly because of the data privacy issue. And also the data annotation is very time-consuming and very expensive. So some existing works, like there are already some interesting research directions try to address this small data challenge, such as data augmentation, and also use weak supervision. For example, use both the language and the images to do the weak cross-model supervision to help improve the detection performance. And we can also use transferring model-based knowledge, for example, transfer learning and meta learning. And of course, we can also leverage some domain expertise. For example, the findings and the definitions from social psychology to provide some new insights to address this small data challenge. And here is a work that about unbiased cyberbullying detection. So I don't have time to introduce it, but basically this work is we don't use any label, and then how to use the multimodality to learn a good representation for a social media session. And as I mentioned earlier, the data annotation is a very important and also very challenging task. For example, currently the data sets, like 77% of data sets are just a binary. So there is potentially a oversimplification problem. And probably we can leverage some psychology and human communication methods to help the data annotation process. And also, when we annotate the data, we embed our own biases or personal values into the annotations, right? So very interesting, there's a work published at ICWSM. It shows that if different people perceive cyberbullying very differently, if you ask an insider, and basically whoever who experienced a cyberbullying behavior before, if you ask them to label the data, they have much higher the probability to label it as a cyberbullying compared to the outsiders or whoever who hasn't experienced cyberbullying before. Last one is causal AI. So I think for all the problems I mentioned, like biases, and even generalizability, and also actually interpretability, all these challenges, not just in cyberbullying, but it's a common challenges in machine learning. I think the key to address these challenges is is to understand the underlying causal mechanisms. So that's pretty much it. And I would like to thank all these generous funding agencies, as well as my colleagues and collaborators, and also most importantly, my advisor, Dr. Huan Liu. Thank you.